Hello everyone, welcome to video 20. This video is going to focus on sequences. This should be a topic that is familiar to you from Algebra 2, as well as if you've been practicing and studying for the ACT and SAT. You do see questions on sequences and series. And so I know it's kind of late in terms of the class, but we are going to start looking at that now. This is kind of the last really true pre-cal foundational material that if you were to take a Calculus BC or take a Cal 2 class, these topics will play a big role in those two courses. So we're going to go ahead and take a look at it. Excuse me. It also kind of builds up again practice in case you're studying for those tests, those standard tests, etc. This is also your second to last video for this class. Everything's been kind of cut and squeezed in to these last two videos, and so let's go ahead and take a look. So this lesson objective, this video objective is specifically just to redefine what a sequence is, as well as look at two types of sequences, which is arithmetic, arithmetic. I always forget to pronounce that way, as well as what's known as geometric. We're also going to define recursive sequences and what that means. When a sequence is defined recursively, we're actually going to look at that type first, and then move into arithmetic and geometric sequences. So let's go ahead and define what a sequence is. So a sequence is an ordered set of objects, typically numbers, something quantifiable. And so again, what it means when we say an ordered set is a set is just another word for list. All right, so we have some kind of list of numbers, and the order matters in terms of, again, first term, second term, third term, etc. So again, the order matters, and it is a list of typically numbers, but it can also be objects. We're going to look at it in terms of numbers. So generally, these are notated, as you'll see, as A1, then A2, A3, A4, and this can go all the way out to AN. Essentially, the biggest thing to kind of highlight here, and this very specific word that I want to focus on, is this word called index. Index, plural, which is indices, is the numbering system in the sequence. So if I wanted to talk about the first term, then what I'm looking for is in the sequence, I'm looking at A1 specifically. If I was to go through and I want to talk about the fourth term, then I'm looking at A4 specifically. And so the index is what takes care of this ordered, this very specific order, labeling, ordering, cardinal system to the sequence. And so what that means then is that the numbers, these little subtext, these indices, are giving me the way that these numbers should be placed. But it also allows me to talk about this, which is known as the nth term. So if we were to go out n times, or this nth number in the sequence, this nth place, then AN would represent that. And so students always tend to struggle with this a little bit just because it's kind of new, but just something I want to kind of really highlight here for you before we get into series and sigma notation, because that's going to play a really important role here. And so some well-known sequences are the odd numbers. So if you were to list 1, 3, 5, 7, 9, etc. The even numbers, 2, 4, 6, 8, etc. You can, sequence could be something like 3, 9, 27, 81. You can notice there's a pattern here in terms of the numbers chosen. Another one would be 0, 1, 1, 2, 3, 5, 8. So if you could kind of figure out what's so important about this sequence, feel free to take a look at it. It's also known as the Fibonacci sequence, to give you a title, and is one that can be used for a project if you'd like to do that. There's also sequence 4, 8, 15, 16, 23, and 42. If you're a fan of a very, very specific TV show that came out when I was in college or high school and college, I would encourage you to try and figure out what these numbers are. And hopefully for my, I guess, pop culture people, that'll kind of ring a bell in terms of sequences. So these are just a few really, really important sequences. Your project assessment that I'll put up will list some other important sequences as you're going through and adding up numbers. And so kind of moving on, there are three main types of sequences that we're going to focus on specifically in this class. One of those is recursive. And so again, this is going to be the first type that we'll look at and kind of define. And then these are kind of where our main world is going to be over the next two videos, which is arithmetic and geometric. two phrases again that are very important in terms of the standardized tests, and then as well as getting into Cal 2 and really talking about area and even Cal 1 in that kind of sense. And we'll do that more in the next video. So let's look at recursive sequences. So we say that a sequence is defined recursively when each term in the sequence is written in terms of the previous term or terms. And so what this means is like, because it's really, really wordy, it's essentially the idea that to get to the next piece of the sequence, we need to use the previous ones. So an example of something like this would say, okay, well, let's say my sequence starts at, say, 1. And let's say the sequence, the pattern was that I'm going to take each entry, so each previous entry, and I'm going to go through and add 2 to it. And that's how I'm going to get to the next term. So in this kind of example, I would start with 1. That's okay, well, to get to the next term, I'm going to add 2 to that. So then the next term would be 3. To get the third entry, I would add 2 to the previous and get 5. Then add another 2 to 5 and get 7, etc. And here, you'll notice we're just getting all the odd number powers. And so we can define a lot of the sequences above recursively. The recursive also can really describe different patterns that aren't the two specifically mentioned. And again, you'll be tempted to use the recursive definition for under the project assessment. And it's one that I would encourage and then hopefully ask you to see if you can find another route to it. So let's take a look at example 1. We'll go through and work through this one to give you some experience with recursive formulas. And then that's really all we're going to do with it. So example 1, using the first term and the recursive definition given, so I'll explain that here in a minute. Let's write the next 4 terms of each of these sequences. And so you'll see 4 different examples here, A through D. And we'll focus here on the first one. And so I'm just going to kind of copy this down so we can take a look at it. So what it says is x n plus 1 is equal to 4 times x to the n minus 10. And then I'm told that x1, so my first term here, is 5. And so if I'm looking for the next 4 terms, then my task here is to find x2. And in the way that this is defined here, this xn plus 1, this index here, this indice, or index, n plus 1, what it's referring to is if I want to find x2, then that means I'm essentially finding x1 plus 1. In other words, notice here that n is 1. So in terms of my formula, this recursive defined expression, equation, however you want to look at it, I would say to do 4 times x1 minus 10. In other words, to find the second term, I'm going to do 4 times the previous and subtract 10 from that. That's how I'm going to get to x2. And so another way to look at this xn plus 1 here is to look at it as saying, if I want to get to the next term, right, this plus 1 piece, I'm going to use the xn, right, the previous one, to get there. All right, and so in order to find each term, we need the previous one, the one right before it, literally. So let's go through and find x2. And so x2 would say do 4 times x1 minus 10. So this would be 4 times 5, which would be 20 minus 10, or just 10. There's my x2. So if I want to find x3, then what this recursive formula is saying is to do 4 times the previous term, which would be x2 minus 10. So 4 times 10 is 40, minus 10 is 30, so there's my x3. And this process can continue as far as I want to go. So I can go to x4. This would be 4 times the previous term. So 4 times 30 minus 10. So 4 times 30 is 120 minus 10, or 110. Now to answer the question, we just need to go one more step. So x5, this is 4 times x4, should be 110 minus 10, 440 minus 10, or 430 as my final. And so here's the next 4 terms, 1, 2, 3, 4, and we've gone through and finished that part of the question. So this is how B, C, and D essentially will work. You'll see the index as being n plus 1. So it's saying if I have the nth term to find the next term, right, n plus 1, then I need to use this equation to go through and find it. So in B, we have y n plus 1 is equal to the previous term yn squared minus 4. And then we are told that the very first term is equal to 0. So another pattern here to notice as we go through is the information that's necessary to solve a recursive formula. Not only do we need to have this form here to find the next term, we have to have or be given some kind of initial term. I have to know something to start with. Otherwise, how am I even going to move forward? All right, recursive, to recur, to refer, to look back, right, to return, I have to use a previous number. So if we're not given that, I can't solve the problem. So in all of these, you will be given some kind of starting point. You have to. So if I want to find the next term, y2, this means I'm doing the previous term, y1 squared minus 4. y1 is 0 squared, which is then just negative 4. To find y3, I'm going to take the previous term and square it, and then subtract 4, so that's 16 minus 4, or 12. This is where our numbers are going to get fairly large. So I'm going to kind of use the work that I've already gotten, so that's why I'm going to kind of go through a little quickly. Make sure to kind of pause the video and do this in your calculator if you need to. So y4, I'm going to use the previous term, which was 12 squared minus 4. 12 squared is 144, minus 4 is then 140. This is why the numbers are going to get massive, because to find y5, my last term to answer the question, I'm going to use the previous term and square it. That's 140, not 150. And then subtract 4. And when you do this in a calculator, you should find that you get 11,876. So 11,876 is your final term. You can see how these grow really, really fast when we're squaring to get to my final answers. All right, so let's take a look at C. C again is Zn plus 1 is equal to 1 over Z to the n. And then we're told that Z1 is equal to 4. All right, so I want to find the next term, Z2. This has to do 1 over the previous term. And so I just get 1/4. Done. To find Z3, I'm going to do 1 divided by the previous term, which was 1/4. Now this is keep, change, flip, which is just going to give me 4, because essentially what this 1 over just means to flip, right? It means to reciprocate. And so I'm just flipping the previous term. So if I want to do Z4, I'm just going to flip 4, which is just going to give me back to 1/4. Do Z5, which is going to flip it again, and I'm right back to 4. So there are my 4 next terms here. All right, now in D, this is going to show you kind of the next level, and it's even, I don't think it's super hard, but it does kind of give you the experience that a recursive can be defined not just based off of the previous term, but the second previous term. So you can use really any number, which is why in this definition here, you'll see now that the term that we can find is Wn plus 2. Well, if I want to find n plus 2, if I want to look at 2 steps down the road, then I'm going to need the previous 2 numbers to solve that. So you'll notice one big difference in this part D here is that I'm not just given the first term as 3, I'm also told that the second term is 5, because we need the previous terms to go through and find each next one. So if I want to find, say, W3, then what I'm doing is I'm taking the one right before it, which would be W2, and then I'm multiplying that by the one before that, which is W1. Right? And you can see that in terms of what I'm adding next to n. Here I'm adding 2, but this one I'm adding just 1, so it's 1 less, 1 before. And now I'm not adding anything, so this is 2 before. And that's why if I'm starting at W3, then I'm doing 1 before, which would be W2, and then the one before that, which is W1, or 2 less. And so I'm just going to take those two numbers that we were given and just multiply those together. So this would be 5 times 3, and so 15 is the W3. So then if I want to find W4, if you kind of recognize the pattern, what I'm going to do is I'm taking the previous term W3, multiplying that by W2. So it's almost like a slider. So this will be 15 times 5. And this comes out to be 75, if I remember right. I'm just going to look at my work. Okay, 75. Perfect. All right. And then we're going to go through, do W5, which would be W4 times W3. So this will be 75 times 15. These numbers are going to get pretty big. Again, pretty quick, so 975. Now this is just the next third term, so we need to go one more time. That's another difference here between the previous two problems. And so this means I'm going to do W5 times W4, which is 975 times 75. Using a calculator, you'll get 73,125. So calculator or doing this by hand. And so there are the next four terms here. And so this is a recursive. Now the only downside to a recursive is that, again, you need to know some previous term. You have to know some kind of initial condition here to get started. And then if a question asks you to find the 50th term in this recursive sequence, right? If I needed to go out to the 50th spot, I would have to find the 49th. Well, to find the 49th, I'd have to find the 48th, then the 47th, then the 46th. You would need to know all prior terms. And so recursive is good, but it's not great in terms of shortcuts and in terms of trying to find some term that's way down the road, because you need to know legitimately everything before that comes before it. And so in the next two sequences that we're going to look at, arithmetic and geometric, there are ways to find these terms without knowing the previous ones. It's all built off of the pattern that we see. And so to start, we're going to look at arithmetic sequences. So a sequence whose terms have a common difference is known as arithmetic. So arithmetic, arithmetic, it's generally arithmetic is adding and subtracting, right? And that's exactly what we're looking at here. So when you're going term by term, there is a common addition or a common subtraction to go from term to term in the sequence. All right, and that's kind of the relationship between everything. So in this problem, given the sequence 1, 4, 7, 10, 13, and 16, what we can do is go through and see that from term to term, so starting at 1 and going to 4, I'm adding 3, I'm adding 3, I'm adding 3, and I'm adding 3 every single time. And so what I'm going to do here is to help in terms of finding expressions in this pattern. If I just go through and label, my first term here, A1, is just 1. My second term was found by doing 1 plus 3. The third term was found by doing 4 plus 3. But understand where this 4 came from. It came from doing 1 plus 3. So notice that in the third term here, I'm essentially doing 1 plus 3 times 2. In the fourth term here, where we got 10, this was found by doing 7, that previous term, plus 3. Well, how did we get the 7? Well, we got the 7 by doing 4 plus 3. Well, we got the 4 from doing 1 plus 3. And again, then, notice how it's just 1 plus 3 times 3. So when I do the fifth term, this was 10 plus 3. Well, we got the 10 from doing 7 plus 3. There's the 10. Well, how did we get the 7? By doing 4 plus 3. And the 4 was gained by doing 1 plus 3. So this means I can represent that fifth term there as 1 plus 3 times 4. So notice how in every expression, this is essentially 1 plus 3 times 0. I haven't added anything yet. And the next one, for the second term, I'm adding 3 once. The third term, I'm adding 3 twice. The fourth term, 3 times. The fifth term, 4 times. So if I want to go down and think of an expression for the nth term, then the nth term, I can look at it as 1 plus 3 times n minus 1. If you notice, what we're multiplying with the 3 each time is 1 less than the term that we're finding. So if n is my term, then I'm multiplying 3 by 1 less, literally n minus 1. And so now I have an expression here that represents any term that I would want to find. So if I want to say find the 50th term, like we were talking about earlier with the recursive, I don't have to go through and add 3 a million different, well, not a million times, but I don't have to add it 49 times. I can go through and use this expression, this general idea here, by saying A50 is equal to 1 plus 3 times 50 minus 1, 1 plus 3 times 49. And if you go through and type this in, 3 times 49 is 147, so plus 1 is 148. So the 50th term in this sequence would be 148. And this keeps me then from having to go through and add 3 a bunch of times to get to this entry, which we could do, but it would take so much time and is so inefficient. So this method, this shortcut here, this formula, gives us a general way to do it. So let's take a look at another type of arithmetic sequence here with different numbers and see if this pattern and everything still sits, so then we can come up with a general expression. So example 2, so given the arithmetic sequence here, negative 2, 2, 6, 10, 14, let's write a function or an expression for the nth term here, an, and then let's determine the 31st term. So if we're looking at this problem here, my first term is negative 2. The second term is negative 2 plus 4. Then A3, which was 6. I added another 4, so we can look at it as negative 2 plus 4 plus 4, or negative 2 plus 4 times 2. For the fourth term, this added another 4, so negative 2 plus 4 plus 4 plus 4, which is negative 2 plus 4 times 3. And then another 4 is added, but we can kind of see what the expression would be. The nth term can be found by doing negative 2 plus 4 times n minus 1. Again, notice the same kind of pattern here, that this is negative 2 plus 4 times 0. This was negative 2 plus 4 times 1, negative 2 plus 4 times 2, etc., where this, what I'm multiplying with the 4 each time, is 1 less than the actual index. So this means if I want to find the 31st term, then A31 can be found by doing negative 2 plus 4, 31 minus 1. 4 times 30, which is 120, minus 2 is 118. So the 31st term in this sequence is 118. And so we found our expression here, we found our function. And so in short, if we're looking at the pattern essentially for this in our expressions, notice that for the nth term here, I'm going to use my red pen, this 1 had a significance. This 1 was the very first term. And we can actually double check that and kind of confirm that by looking in our example 2 here and seeing that the very first term that we're adding is the very first term in the sequence. What did this 4 represent in this example? What did the 3 represent in this example? All right, well, those were the common differences in each to go to each term. And so notice here I've got my first term A1 plus the common difference times n minus 1 in both cases. And so this gives us now a generic way to represent any kind of arithmetic sequence. So if I have an arithmetic sequence that's A1, A2, A3, all the way to AN, that nth term there, we can express the nth term as AN is equal to, I'll write it this way, A1 plus D times n minus 1, where A1 is the first term in the sequence. D is the notation I'm going to use for the common difference. Because remember that if this is arithmetic, then each term is found by either adding the same number or subtracting the same number every time. And so that's what the D here is going to represent. N again represents the number of terms, or that term that I'm looking for, and then AN is that specific term in the sequence. And so that's arithmetic. That's the equations for that. Now something very interesting about it, and I just kind of want to point out this connection, it's that if I have an arithmetic sequence like this, this formula here is actually very, very similar to something. And so what I'm going to do with it is go through and distribute the D. So I get D times N minus D. And then I'm going to bring the A1 and this minus D together. So I get D times N plus A1 minus D here, because this is just a number. D is that common difference. So as my index keeps going up by 1, like what is that change? And N is essentially like my input. Well, another way to kind of look at it is in the form of y is equal to mx plus b. It's the same format. M represents the slope, right? The change, right? As this one value is increasing, how does my overall sequence, how does my overall function increase? X is the term that I'm looking at. And this expression here, A1 minus D, is my initial value. It's my y-intercept. In other words, when n is 0. If you look back at all the sequences that we've done so far, my n has always been 1. But can n be 0? In other words, can you have a 0? And that can happen. In physics, you see this notation a lot. It's the way of essentially saying initial value. And when x is 0, what you're finding graphically is the y-intercept. And if you were to subtract d from our very first term in these sequences, then what you're finding is the previous term from A1, which has to be A0. And so that's what that B essentially represents. So this is just another way to go through and write the function and the expression for that. All right, and so I've got one last type of sequence and one example to look at, and this video and topics are done. So that topic is geometric sequences. So this is a sequence whose terms have a common ratio. These are called geometric. So an example of this would be 3, 6, 12, 24, 48, 96, etc. Where, again, when we say common ratio, what we're talking about is a common multiplier, which we abbreviate with an R. All right, there's something that is being multiplied each time to get each entry in the sequence, each term. And so how you can find that is essentially comparing or setting up the ratio between the first two terms, the next two terms, whatever. It just needs to be one term in the previous or one term in the next. And setting it up in terms of 6 divided by 3, which is 2. This is my R. So if you want to set up kind of a formula to find R, how we can do that again is by doing, say, A2 over A1, A3 divided by A2. That is the correct setup to finding R. Another times you can just look at it and find out what it is. All right, so this is how we can look at it. All right, so that means you can see down here a geometric sequence can be expressed as AR squared, AR to the third, all the way out to AR to the n minus 1. All right, and what this is doing here is instead of saying A1 as my first term, we can just say A, because that A is just going to be multiplied by the same value each time. To help show you this, using the previous example, my first term here, A1, is just 3. My second term is found by doing 3 times 2. The third term is found by doing 3 times 2 times 2, which is 3 times 2 squared. The fourth term is 3 times 2 times 2 times 2, multiplying another 2 on there, which would be 3 times 2 to the third. So like before, you can kind of see the counting, how if my index is 4, I'm actually only multiplying by 2 3 times. If my index is 3, 2 times, 2, 1 time, once, 0, right? I'm not multiplying by 2 at all. So if I want to write an expression then for the nth term, this would be my very first term A1 times R to the n minus 1. And that's why you see A R to the n minus 1 listed here. Now, because A1 stays consistent, we don't need to give it an index. We'll just call it A. It's whatever that initial term is, whatever that first piece is in the problem, the sequence, that first entry. All right, so what we'll do with this is determine the common ratio for an example 3, and then find the next 3 terms. That's really all about what we can do with the geometric sequence. This will play a major role when we do series and sigma notation. So if I want to add all of these numbers together, what can happen? And you'll see a lot of questions on your project assessment that also accompany this. So let's go through. So in A, I've got 1, 3, 9, and 27. So one way to find R is to do A2 over A1, which would be 3 divided by 1. So my R is 3. That's the common ratio. And so if I wanted to find the next 3 terms, I have 27. So I'll just multiply that by 3. So 3 times 27 is 81. Multiply 81 by 3 is 243. Multiply 243 by 3 and get 729. So there's the next three terms in the sequence. So pretty straightforward. The R and B, I'm going 64, 16, 4, 1. Again, I can find it by doing A2 over A1. So 16 divided by 64. Notice then if I simplify this, this becomes 1/4. So I'm actually multiplying by a fraction here. And this is why ratio is such a key word and not just like multiplier, because that can be kind of misleading that you're thinking I'm always going to be multiplying by 2 or 3 or 5, like it's got to be a whole number. But that's not true. Like your ratio can be a decimal, it can be a fraction, it can be anything, right? You're just multiplying by the same thing each time, the same real number. And so here, R is 1/4. So if I want to find the next entry starting at 1, 1 times 1/4 is literally 1/4. Multiply that by 1/4, I get 1 over 16, and then 1 over 64. There's the next three entries in this sequence. All right, what about C? All right, so if I want to do C, I have -5, 25, -125. So notice how I have negatives involved. Well, because I'm multiplying, that just means my ratio must have been negative. And that can be found by, again, doing A2 divided by A1. So 25 divided by -5. I get R is literally -5. So the ratio that I'm multiplying each time is negative. So if I have -125, then the next entry is positive 625. The next entry would be -3125. And then the last entry that we need to find would be 15,625. And so here is my answer for the final three entries of the sequence. So that's it for the sequences. So again, the three main types of sequences that you can see are known as recursive, arithmetic, which is addition and subtraction, and geometric, which deals with multiplication and division if you think about it in terms of fractions. So when I do arithmetic, I remember this is when I'm looking at a common difference. This difference, again, could be negative, right? We only looked at positives, like adding 2, adding 4, etc. But that D can technically be negative. For geometric, it's all about finding that common ratio R, where R is a ratio, it's a fraction. So it can either be one that you're multiplying by a number greater than 1, so it's going to be a continuous growth, or your R is a fraction less than 1, and you have decay. Your numbers in the sequence are going to get smaller and smaller. And so in closure, those are the types of sequences. These two will play a huge role in your assessment, as well as when we're looking at series and some applications of that. So if you have any questions, definitely let me know. And one more to go.